Hello. So in the previous videos, I explained the basic underlying structure of estimation and statistical inference, population sample, parameter, statistic, and what cannot be an parameter, what cannot be an estimator. Now we are entering the main issue. What is a good estimator, or how can we evaluate the performance or the accuracy of an estimator? So, first thing you have to understand here is that an estimator is calculated from a sample, like sample average, sample probability, sample standard deviation, whatever you calculate from the sample. And we learned in the previous chapter that random sampling can be understood as one experiment. So you calculate an estimator from a sample. And then if you resample again, then recalculated estimator can be different from the earlier one. Therefore, an estimator is random. That's what we learned in the sampling distribution chapter. So, like if you get a different sample, then your estimator will be different. Therefore, if you view the random sampling as one experiment, then the estimator is the outcome of that experiment. So it is random. So we can think about its distribution. That is the sampling distribution of the estimator. And that is the basis of our evaluation. So we will tell if an estimator is good or bad based on the estimator's sampling distribution. For example, here, a simple example, a perfect estimator has this property. So estimator is theta hat is random, and theta is the true parameter. So if the estimator equals the true parameter with probability 1, so the probability that the estimator is correct about the parameter equals 100%, then this is the perfect estimator, right? Then where is this probability from? The probability is calculated based on the sampling distribution, right? The sampling distribution of the estimator. That means this probability is calculated even if you resample again and again and again, every time your estimator will be perfect. So the evaluation is based on the sampling distribution. So let's use a graph. Suppose that true parameter is here. This point is the true parameter. And then your sampling distribution for the estimator will be a normal distribution like that, usually. And so in this course, I will say a normal distribution. Like in advanced level, at the advanced level, there are some exceptions, but just let's simply consider a normal distribution. So your estimator, if your estimator is reasonably good, then it will be distributed like this around the true parameter, right? So it may happen here, or it may occur here, or here, anywhere with some probability, but naturally most probability will be close to the true parameter, and extreme errors will be small. So for example, suppose that your estimator happens to be here. So your estimator is realized at this point. Then the distance, your true parameter is here, your estimator is here. So the distance is the estimation error, right? Right? But the distance, of course, the error is also random because your estimator may realize at a different point. If it realizes at a different point, then error will be different. Error can be 0 or can be negative, can be positive. So this is so error is also random. And then some examples to evaluate the estimator. For example, like we say, if the estimator is greater than the true parameter, then we say the estimator is overestimating. It's overestimation. So estimator is greater than the true parameter, and its probability is this shaded area, colored area, which will be 50% because it's half and half. So 50% is the overestimation probability. So if you know the sampling distribution, you can calculate that. Similarly, right? Exactly, you can use the underestimation concept. Like if the estimator is smaller than the true parameter, you are underestimating the parameter. So this is the probability of underestimation. Underestimation probability is here. So shaded area, which is also 50%. Or you may think it this way. You may be interested in this kind of probability. This is the probability of estimation error smaller than a certain value. Say, what is the probability that the estimation error is less than, say, 1? Plot between plus minus 1. Then say minus 1, plus 1, and the area is that probability. So like this, if you know the sampling distribution of the estimator and the relative location of the sampling distribution and the true parameter, then you can evaluate how accurate your estimator is. So everything depends on the sampling distribution. Here are, so now what we are going to do here is there are two candidates for estimation. So you would like to estimate a parameter, and there may be many different types of estimators. Now we would like to compare them. How can you compare them? Of course, the comparison is also based on their sampling distributions. So think about blue estimator and orange estimator. So if you know that the true parameter is here, and then if you compare those two sampling distributions, what you can tell here is that the orange estimator tends to overestimate. It's centered around most probability, the maximum probability, highest probability is away from the true parameter. So the blue estimator is correctly centered around the true parameter, but the orange is not. So the orange is toward a larger value. So it's overestimating, which is not ideal. So if you compare these two estimators, I would choose blue. Blue is better. And now, what if you have these two parameters, estimators? Blue estimator has this sampling distribution, and green estimator has this sampling distribution. In this case, both have the correct center. Both are centered around the true parameter, which is good. But the major difference is the variance, their variance. Green is more spread out, and the blue is more concentrated around the true parameter. That means the green estimator tends to have larger errors. It has larger error like this. With larger error has more probability. But the blue estimator has more probability around the true parameter. So the comparison is obvious. The blue estimator is better because the estimation error tends to be smaller for the blue sampling distribution. So these two are a simple graphical illustration of how we compare estimators. Now we are going to formulate them into two criteria. Number one is about this comparison. We are interested in if the center is correctly at the true parameter. The center of the estimator's sampling distribution should be at the true parameter, which means the expected value equals the true parameter. So the center is an interpretation of the mean. The expected value of the estimator should equal to the true parameter. That was the first criterion. And the second criterion is about the variance. Like this. So obviously, as long as the center is correct, the smaller the variance is, the better the estimator is. So as the variance increases, that means the tails are thick, which means larger errors are more likely. So, excuse me, if you compare these two, blue is better because the variance is smaller. So the smaller, the better, right? These are two important criteria for good estimators. Also in advanced statistics, there are additional other criteria, more theoretical criteria can be like some textbooks have other criteria, but I'm not going to cover them because they require additional theoretical discussions. So I'm going to skip them. We are going to consider only these two guys, these two criteria, which is still very important. Clearly, they are the most important criteria, and it's not easy to understand them right here. So, okay, so far, it sounds obvious. So when I explain, when you watch the video, it sounds like it's obvious, right? That's good, but actually in practice, it is not easy to tell if the expected value of the estimator is the true parameter or not, and if the variance is small or not, because first, the true parameter is unknown. So how can we tell the expected value of the estimator equals the true parameter without knowing the true parameter? That is the first problem. And second, how can you calculate the expected value and the variance of the estimator? To calculate them, we have to have repetitions of the observations. So we have to have multiple random samples, but we don't have. So these two criteria should be studied purely theoretically. So they are purely theoretical properties, and in practice, you have to understand the theory first to tell what is the best estimator, right? What is a good estimator requires theoretical discussion. So otherwise, we cannot see what is good. So when I ask you what is the mean gas price, then someone may say $1, someone may say $10. How can you tell which is the correct one? In practice, it's not possible, but theoretically, it's possible using the sampling distribution theory. So we are going to study these two criteria in the next slides and next video. And yeah, I will stop here. Okay, we'll see you in the next one.